Hey, welcome back to the last chemical bond type in physical science. We're going to go over, we went over ionic bonds, which went on between a metal and a nonmetal. And then we went over covalent bonds, which goes on between two nonmetals. And of course, the last logical one is the chemical bond that occurs between two metals. Okay? Now, the only thing you got to know about this is how a metallic bond works. You're not responsible for having to be able to write a chemical equation and figuring out the different kind of alloys. If you want to learn that kind of stuff, you really should take and sign up for the full-fledged chemistry class. All right, let's get going. Make sure I'm going to go ahead and cook along kind of quickly, so make sure that you stop it as you need to in order to keep your notes complete. Always be prepared in case I ask you to send me a copy of your notes, because every once in a while I'm going to ask for some bonus points and I'll ask you guys to turn in your notes. Okay, so always be prepared. All right, of these four things, yes, I'm sorry, you're going to have to write all four of these down. There's lots of things to say about metallic bonds. I've boiled it down to four main bullets, so let's go over those. You remember what valence electrons are, right? Those are the electrons in the outside shell. The farthest outside shell that an atom has of electrons, those are called your valence electrons. Well, it turns out with metal atoms, they hold on to those electrons very loose. Okay, so loose. They just barely can hold on to them. They're just barely floating around in that outside ring. And that takes us to bullet point number 2. They're hold on to so loose that they can actually pop off of one, or they say roam off of one electron shell from one atom and actually float over and join into another outside valence electron ring on another atom. Okay, so these loosely held valence electrons just kind of float back and forth, around and around, all around these different atoms that are bonded together in this chunk of metal. Okay, third thing, and notice this is in quotes, chemists often describe the metals as consisting of metal ions or nucleuses or nuclei floating in a sea of electrons. And when you write that down, make sure you write down the term floating in a sea of electrons, and make sure those words you underline, make them really bold, really strong, circle them, put hearts, stars, whatever it is that draws your attention to that in your notes. It's very important you remember the term floating in a sea of electrons. That's a key definition that they use, always associated with metallic bonds. The last bullet is those free-roaming electrons are not only responsible for part of the metallic bond, but we use those free-flowing electrons to actually carry electrical current. So when we hook up a battery to a wire or to a circuit, those free-flowing electrons are just kind of wandering around from, let's say, from copper atom to copper atom. When you hook it up to a battery, we get all those free-flowing electrons to flow in one direction only. Okay? Or if you hook them up to a wall socket, you get AC, which means the electrons flow one way, then the other way, then this way, then that way. They all flow together back and forth, back and forth. Okay, so on to the next slide. There we got a good example of metal bond. There you got a good blacksmith working in there. Okay, now this chart right here, I need you to go ahead and copy that down. You may have to pause the video once in a while, but you definitely want to write this down. We're going to need this for our next lab. Our next lab, I'm going to give you various materials, and you're going to heat them up with a blowtorch. And you're going to figure out if they melt with the blowtorch or if they still stay a solid. Now, look across the very top of the chart, you'll see ionic, covalent, and metallic. We're going to be able to tell by heating these chemicals up as to whether they have an ionic or covalent or metallic bonds on them. Now, something with an ionic bond like table salt, I don't know if you ever tried to melt table salt, but it's not too easy. You have to have pretty high temperatures to melt salt. That would be an ionic bond. Covalent bond would be something, let's say, like sugar. Sugar cube is all covalent bonds. If you try to heat up sugar, of course, it doesn't take much to get sugar to melt. And then we've got a metallic bond, like if you're trying to melt steel or copper, that takes quite a bit of temperature, pretty high temperature to get that, and we're not going to be able to do that in our little lab that we've got. Next row down is conductivity. That tells you how well electricity flows through that material. Now again, let's use table salt. Did you ever try and get electricity to flow through a cube of salt? Not too easy. Yeah, like it says right there on the chart, it says pour as a solid. But down below that it says it's pretty good if you melt or dissolve it. So if you take salt and you put it in the water and you let it dissolve, well, now an ionic bond will actually, the salt will actually allow electricity to flow through pretty well. Next thing over in covalent bond, sugar, I mean, you can get some electricity to flow through it, but it's very, very poor. And of course, metallic like copper and steel, you can get electricity to flow through very well. So it's got really good conductivity. Now, malleability down there at the very bottom row is if you were to take a hammer and you smash down on this mineral, if it shatters, then that means it's a very poor malleability. But if you can hit it like some sort of chunk of copper or lead, and you can just shape it into different shapes, and it doesn't splatter and split all over the place and shatter like salt or sugar does, then that means it's got really good malleability. And like the examples I just showed you, an ionic bond, like with table salt, hit that with a hammer, of course it's going to shatter. Same thing with a covalent bond, like the sugar. If you hit that, it's going to shatter, split all over the place. But something like metallic, like copper or aluminum, you hit that with a hammer, you can shape it into different kind of shapes, and it won't shatter and go all over the place. All right, next slide. I wanted to show you you don't have to copy this down. I just wanted to show you that when you form a crystal like table salt is made up of sodium and chlorine, and that's what I've got shown here on the screen. We've got some sodium and chlorine ionic bonds that have all kind of been bonded, but they're all just scattered all over the place. Let's say they're mixed in with some water. Now, as you let that begin to dry and the water goes away, those sugar crystals will the salts will actually begin to crystallize and form salt crystals. And when they start to form that salt crystal, it actually forms a pattern, and that pattern is called a lattice structure. That's the title at the top. Okay, so I want to show you how these all line up. Notice that the NAs in blue, that's the sodium, that's actually a positive charge. Remember, our metals are positive. And our nonmetal right below that is the chlorine. Okay, and the chlorines are negative, it's a nonmetal. Now, if you look at this and you start moving these together, you can actually fit these all together so that around every positive there's a negative, and around every negative chlorine there's a positive. So when these all come together, it forms, you can see, a nice cube. Okay, and that's what they refer to as a lattice structure. Now, we were talking about a minute ago is that it has very poor malleability, which means if we take that hammer up there in the corner and we hit that crystal, bang, of course you know that that crystal is going to crack. It's going to separate. It's going to shatter. And I want to show you why that happens, why that crack actually propagates through that salt. And if you look at that where it hit, see now the chlorine, the black chlorine circles are right across from each other, and the positive sodiums are across from each other. And we learned before that opposite charges attract. Well, like charges, like two negatives or two positives, they repel each other. So all of a sudden it splits and it comes apart. Okay, and that's how the crack actually begins to propagate down through the crystal or the lattice structure. And this right here was supposed to be a nice little picture simulating the sea of electrons, which is not a very good slide on there. I apologize. It used to be hooked up to an internet site, and that was all nice little animation in there for you. Okay, now the nice thing is writing chemical formulas, you do not have to, only ones you have to know have to be able to write chemical equations for, in this module, is oxidation, or excuse me, not for oxidation, but for ionic compounds. Okay, so the only thing you have to remember about covalent and metallic bonds are how they're formed, and make sure you remember the definitions for them. Okay, have a great day.